Can we start? Okay. All right. Let's start. Today we'll talk about the trend, detrend. Trend is a very important property of the data, especially non-stationary data. And I remember when I first embarked on this work, there's standard detrend. If you use MATLAB, you take data as a detrend x. What MATLAB will do is draw a straight line through the data and take the mean away. And people mostly use that. Now, when I first embarked on this work, I used Google. I typed the word trend. To my amazement, it's come out 100 million hits. In other words, there are lots of people interested in trends. Of course, not all the trends are concerning data. Trend can be trendy, fashion trend, or whatever. But the trend in data is really critical. Not only it's a intrinsic property of the data, but it's also a part that in doing something else, you have to take it away. Like, for example, you do a spectral analysis. If you don't take the trend away, then you have a huge DC components, and that may swamp all the other data. And especially if the trend is really strong, then that trend itself in Fourier analysis can cause all kinds of harmonics. And so that can swamp all the data. So we're going to talk about trend and detrend in this last part of the EMD. And for those are interested in reading this in print, this is in Proceeding of National Academy of Science. It appears just appeared last year. You can get this paper, and if you cannot download this paper, come to my office. We'll give you a copy, or I will bring several copies next time to give out to you. But this is only a part of what we're discussing. When I was working for NASA, this actually struck me very amazingly. Struck me just unbelievable that people handling data this way. What this is actually a satellite altimeter. You use a satellite, you measure the height. And then you use satellite measure the height of what? Of Greenland. So Greenland has a lot of ice. If the Greenland ice all melted, then the global ocean level is going to increase. So people pay a lot of attention on Greenland ice. So then at NASA, we use altimeter to measure the surface contour of the ice. And here are the data you got. Point here, point here, point here. This all the crosses are data. And they will try to find out a trend, because this is the game in town. That is global warming. If I can find out a trend in the data, then I can say, aha, the global is warming. Look, here is a trend or whatever. Okay, but the data is so noisy. Jump from here to there. So once people get this data, I start to get a paper to review. There are people start to using this data to compete. Who can draw the best line through them? There actually is only one line that you can draw, a straight line. So that's this line. But my colleague at NASA is the chief scientist for a satellite called IceSat. The satellite is dedicated to measure ice. Okay. And he got the data because people has already joined in the fray or joined in the computation in drawing a straight line through the data. So he thought he would do something different. That something different is this. Then in addition to this data, he put a sine curve on that. Why put a sine curve on that? The sine curve represents the seasonal change. So In summertime it's lower, wintertime is higher, and so on and so forth. He's trying to do that. He thought, if in addition to a straight line, if I put a sine wave, then I have much better chance to fit the data. Just in case this fluctuation, some of the fluctuations are indeed annual fluctuations. And so when you get when you go through this exercise, what you got? You get a slope of that line, and you get amplitude of this sine wave. And he was very proud, and and this becomes one of one of his major accomplishments. When I look at this data, then another data come to my mind. So if we get data like this, that's also data. How can we draw lines? Should we draw straight lines through here? Straight lines through here? This data the trend looks the same, but they are not the same. This is a global surface temperature warming. This is NASDAQ stock market. And people may think, well, the stock market increase is caused by global warming. That's not not true either, because this data span is from 1860 to present. This is 1984. This is much shorter data. So on this data, you cannot draw straight line. On this data, this particular data set, even though we think that they should not draw straight line, but that did not prevent people from drawing straight lines. Yeah. The figure that I show here is a Nobel Prize winning work. This is a Intergovernment Panel on Climate Change, IGPP. This data actually are the original data. This black dots are original data. Then this annual mean, and then a smooth the series, and and the error bar around the time series. Okay, so you smooth by running mean, then you compute the standard deviation, and once you finish that, then what do? You draw lines. You draw one line. This line is 150 years average trend. Then people say, well, that's not very serious. This is very gentle. Okay, we'll draw another line. From here to draw over there, that's 100 years line. This is steeper. That's still not very serious. So then you say, okay, I'll draw still another line. That's 50 years. And then it's 25 years. And exactly what is the trend? Yeah. So apparently, people, by using different time scale, people get different trend. And also, people always get straight line. Yeah. Now my question is this right? Then, after I look into the survey, who actually is more worried about trend, I find the economists worry about trend even more than us, because economy is never stationary. If the economy is stationary, then our income will not grow, and as population grow, and our income will not grow, total national product not grow, then we have serious problem. So the economist has this annoying problem of trying to find a trend. Everybody's trying to find it. The most famous person that's dealing with this are Ingalls and Granger. Sorry. Ingalls and Granger are not common people. They walk on water. They are Nobel Prize winner, 2003. And if you don't believe me, just go to the campus. There's a chair, Ingalls and Granger, right behind the Student Activity Center. Yeah. Ingalls and Granger, in this long-run economic relationship, this book published in Cambridge University Press, say one economist's trend is another economist's cycle. So obviously, they have problem defining trend. You say this is trend. I say, no, this is not trend. This is a cycle. Oops. All right. So exactly what is a trend? That's all right. I don't have to see them. As long as they can see this. Can they see this? 那就可以。没关系。That's good. That's okay. That's okay. So with this problem, then Engels and Granger introduce a new concept. This is a simple trend. It's a straight line. That he agreed that like you draw a line from beginning to end. That's a simple trend. But then he introduced a stochastic trend. What's a stochastic trend? Stochastic trend is still straight line. But this straight line does not go from beginning to end. It goes from one quarter to another, just within one quarter. So you take the data, you divide the data into quarter. Why you divide it into quarter? Because all the business people report their activity quarterly. So each quarter you draw a straight line. Now this line, these lines, so each quarter has a straight line. Then you can see that this line does not go through the whole data and it's go up and down, but it's not a continuous line. It's a broken line. Yeah. So this quarter looks like this, next quarter may look like this, and third quarter may look like this. Yeah. So it's totally discontinuous. Now, the reason that you have this problem, and you have this problem, is exactly the problem that I think that anticipated by ancient Chinese. His name is Confucius. Yeah. What he said is 名不正则言不顺，言不顺则事不成. Yeah. 名, I'll come back later. First, let me give you the translation. Translation is, without a proper definition, logic discourse would be impossible. Without logic discourse, nothing can be accomplished. Yeah. What it is a Ming, is name in Chinese. But Ming, the other connotation is that Ming is also definition. It's a name, it's definition. Not only that, Ming also implied logic. In the turn of the last century, when the Western knowledge, Western civilization, culture start to be imported in China, the subject, logic, how you translate the word logic into Chinese. The first translation is 明学. 明学 means logic. But then people say, well, that's not very good. So finally, everybody give up. Says, I cannot find a proper translation. Let's just translate to 上, 逻辑, logic. Yeah. Why Ming imply logic? Because in ancient China, there was a philosophical discourse, 白马非马. This is a horse is a horse, but a white horse is not a horse, or a horse is not a white horse. So this kind of argument means that the definition is important. The name you give to a subject and the subject itself has different meaning. So you have to sort this out, clear the definition. So if definition is not proper, then the yan means speech, discussion, cannot be smooth. And without smooth discussion, nothing can be accomplished. This is exactly what Confucius said. Now, obviously, what we need is a definition of trend. Is there a proper definition of trend? Has those experts, leading experts, give us a definition? I haven't seen it. Yeah. So without that, this is my attempt to give a definition. The definition of trend is within a given data span. When we talk about trend, we have to talk about the data trend, that a span of data. Okay, different span, different length of data may have different trends. Okay, the trend is an intrinsically determined monotonic function, or a function in which there can be at most one extrema. What this means? Here are a couple of important words. Intrinsic. First, we have to have a data span. That means trend is a local property. Yeah, this property works only for that particular data span. Once you go beyond that, it may not work. Then another word is intrinsic. Intrinsic means it belongs to the part of the property of the data. This intrinsic is against extrinsic. Intrinsic is objective. Intrinsic means that I come in here, it's determined by the data. Extrinsic is I don't know, I don't care what the data is. I determine it for you. Okay? If you determine for the data, that means you can impose the trend on the data a straight line. If you argue with them, so why straight line? So all right, I'll give you a polynomial. Then why polynomial? Why it's not exponential? Yeah. So this extrinsic means you have to determine a subjective functional form. And that functional form, unless you know the physical property of the data, there's no way that you can come up with a subjective functional form. And that is what my objection is. So trend has to be local. You have to talk about the data span. Now once you take the data span, you cannot a priori determine the functional form of the trend. The trend is intrinsic to the data. If you have to do that, that means the method that you use has to be adaptive. And more, the final trend is a monotonic function, or a function that has at least one extrema. And what that reminds of you? That reminds you of empirical mode decomposition. If you have two extrema, then I can plot a cycle. So if you leave two extrema in that, then people say, well, that's the cycle. And that's why the economist always argues, well, this is the trend, this is not a cycle or whatever. So the definition of trend is local and intrinsic. What you have to do is that you take away all the oscillation away. The part that is not oscillating is your trend. Yeah. Now how you take the oscillation away? There are many ways. That I think the preferred way, the adaptive way, is empirical mode decomposition. Yeah. Now once we have the trend definition given, then we can look at this. What is the D-trend? D-trend is a very important operation too. If you type D-trending, you also hit almost millions of people try to D-trend. The D-trend, once you do D-trend is within the given data span. D-trend is the operation to remove the trend. You take the trend away. And what's left is the variability. Yeah. When you say variability, you have to have a reference. This reference is you vary from what? Okay? In the past, people discuss variability always refer to the mean. Yeah. Mean is fine if the data is stationary. I can have a mean. But if my data is non-stationary, and especially if my data has a trend, then you cannot just force the data into the mean. Yeah. What kind of data that the mean does not make sense? There are lots of them. The most common one is the stock market. You cannot calculate stock market variation from the mean. You calculate the stock market variation from a trend. Yeah, because it's moving every day and it's always growing or sometimes decay a little bit. But long term, there's no problem. So trend and the D-trend, they are the same thing. That is, you have to define the trend right before you can take the trend away. Now, before people understand the trend, and people has the need of take the trend away, D-trend. So what are the common D-trend methods? The traditional D-trend methods, there are many. The first one is differencing or differentiation. What's the differencing? So if my data has all this up and down, up and down, up and down, I take data x n plus 1 minus xn, n plus 2 minus n plus 1. Yeah, you take the difference between the data. Immediately the trend disappears. Okay, but you change the property of the data. Yeah, you may very well take the trend away, but you have not solved your problem and say, if you want to find out what is the trend. Once you take a differentiation or differencing, you still don't know what the trend is, even though the data may look flat. But that flat data has very different meaning than your original data. The other one is regression. Regression, however, implies some subjectivity. That is, when you start to regress, you want to find the best fit curve. What is the best fit curve? That means the variance from that curve is minimum. So you have to start with a curve to begin with. Which curve should you use? Should you use straight line? Straight line is the most simple and easiest to implement. So many people just use straight line. Yeah, like the other Nobel Prize winning work on global warming. It's a straight line. Yeah, but that's regression. Once you pick up a functional form, then you can move that functional form, juggle that functional form, twist that functional form to make the functional form fit your data best. Once you change that functional form, you get another answer. So that trend is not objective. In other words, when you do it and I do it, we'll get it different. Another way is filtering. I run a spectrum of the data. Then let's say that frequency lower than certain value, I don't care. I only need those low frequency components. I filter out all the high frequency. But if your data indeed has a trend, you can go back and try. See, if my data looks like this, and you do a Fourier spectrum and try to get rid of that, you'll never do it right, because the jump condition from beginning to end. So these are the traditional methods. And what I suggest is that I think we need an adaptive method. Now, this adaptive method is we know the adaptive method. It's EMD based. We do this, go through, we get C1, and finally we get this X equal to summation Cj equal to Rn. Rn is of course a trend, but that is an overall trend. The trend that I'm talking about here is more than just that last residual. The last residual is an overall from the beginning to end trend. And there are other trends that we can get. But the other trend, however, we have to attach a time scale to it. So when you talk about trend, there are two parameters that I have to give. One is how long, for how long, what's the data span? And then once you define the data span, then you can talk about the trend. So let's revisit the residual. The residual is overall trend. Trends arrive through remove all the oscillation. Yeah, not through averaging. So if you do averaging, you actually select a time scale. But by removing oscillation, we don't select time scale. We let the data decide. So in this way, once we get it decomposed, then we can define trend not only for overall, but we can define trend for other time scales as well. So let's see these two data. We'll look at the temperature data first. This is the temperature data. And the temperature data, I decompose it, I get this many components. And this component, these components, and I tried different stoppage criteria, and I got many different trials. And once you get this many different trials, you get a mean, which looks like this, and you get a standard deviation, which is very tiny. So this data is very benign, very nice. It's not very pathological. When you go through the process, you'll find that hey, this data is the standard deviation is small. The only standard deviation is not small are the last few components. It has a very large n swing. But this n swing is 10 to the minus 3. It's again small. Yeah. Now let's see. And if we plot the periodicity against the IMF variation, we find that the first components, the period is this, the second is this, third and fourth, and then it starts to pick up. I try to use the statistic significance method, but I find that's not very good because the statistic significance method was derived based on white noise. The white noise is statistically stationary. Here, our data is not statistically stationary. So instead of you plot that upper bound, lower bound, I use 3 sigma as the standard. So if it's beyond 3 sigma, then I would think this is a significant data. So here we find at least the last two are way away from the possible of white noise. So let's use the last two. The last one trend looks like this, and the standard deviation, it's here. It's that small. And standard deviation is only discernible at the end, but it's tiny in the middle section. Yeah. So the standard deviation plot against the mean versus data, you can see 95 percentile standard deviation is very small. So this decomposition is quite stable. If we use this as trend, and this trend is much better than the straight line plotted by the IGPP, Intergovernmental Panel of Climate Change. That's their straight line. This is my trend. And not only that, if we have used this curve, then we can compute its slope, the rate of change. The rate of change in the intrinsically fitted data, it's a curve. It's not a constant. So a curve gives you increasing rate look like this, and whereas the straight line fit gives you constant rate. Okay. Whether it should be constant rate or the curve, we can see it very clearly from the data. Yeah. when I show this to, perhaps I told you, when I show this to you, the NASA administrator told me, so, "Oh no, you don't want to talk about this because usually they will go in front of the Congress, U.S. Congress, to make testimony." Says, "Okay, we find that the Earth is warming up, and warming up is like this." Then they get lost. Why? Because he said that the average congressman's math background is about 4th grade. Yeah. So they only know one number. If you give them numbers, it's each year increase that much constantly, they understand. They say, well, at the beginning increase very slow. Now we're increasing, accelerating, because people burn more gas in the 1980, 1990 versus 1860. 1860 has no car on the road, no plane in the air, and no mass production, big factory, large power plants. Yeah. So at that time, the temperature increase is very slow, and now the temperature increase very fast. That makes physical sense, but that does not get through easily to a person without quantitative training. Yeah. But of course, I'm biased. I prefer this slide. Yeah. Now, if we take data away from that trend, this is the variability. Take away from the curved linear trend, this is the variability. In this variability, you can see some wavy forms. Yeah. So this wavy form, they implies another cycle. Sure, there's another cycle. If you put 2 components in there, then you will get this curve. You'll get this curve. That will go through the data. Beyond that, however, I cannot tell whether it's noise or statistically significant trends. And if you put the two components together, you will see the standard deviation increase a little bit more, but it's still small. So this trend is still statistically significant. Yeah, and this trend is interesting because the temperature will first come down and pick up again, and come down, pick up again. This coming down around this time in the 60s and 70s, if you care to look back, if you go to, if you have time, you go to the library and you check 60s and 70s. Are there any people talk about global warming? No. People talk about we're going to ice age. Yeah, because the temperature is keep decreasing, and then suddenly after that we start to warm up. So people start to say, "Oh, we have global warming." Yeah. So whether it has a global warming or whatever, are influenced by this subtle change of a curve. If you plot, say, like 10 years, each year is colder, and then you look at the data and say, gee, the climate is dictated by Milankovitch cycle, then maybe we're heading to an ice age. Yeah. So this is what we got. And if we get this, then the variability, then then we have this linear trend, we have this overall trend, and we have this as a more local trend. As I said, if you code this trend, you have to tell me a time scale. So what is the time scale of this of this trend? The time scale of this trend we can calculate. And first you can calculate the rate of change. This rate of change is much stronger than that because it's more local. It fluctuates up and down. If you take a difference or differentiate the data, of course the slope is even stronger. But this slope is much, much stronger than this. In other words, the rate of change fluctuates much bigger. And the time scale That means if we measure the measure the wavelength of that. Next time I will talk about how to measure the time scale of this. The time scale is average on 65 or 66 years as mean. So there is a roughly 60-year cycle in the climate data. Why it's 60 cycle? What is the driving force for 60 cycle? 60 years cycle? No one knows. And when I discussed this at Caltech, a professor there said that the ocean temperature seems to have this cycle, but I have not seen anything published clearly and clearly articulated. So this is just an observation. So this is around a 60-year cycle. Once you take away that, this is the variability. This is the variability. Okay, from that 60-year cycle. Many people think that the global warming is serious, not only because it's warm, but also once the global warming start and the atmosphere or our global system will have more energy. And this more energy implies large fluctuation. So we'll get hotter, and we'll get when it's hot, we get hotter. When it's cold, we get colder, and the hurricane is going to be stronger, and so on and so forth. So, for example, if you look at the original data, original data, they will call this 1998 the hottest day, hottest year on record, and that proves global warming. But this hottest year single out because the fluctuations sit on top of an already upswinging curve. Whether the variability is large or small, that's a totally different story, right? The variability, whether the variability grow with climate, we can look at this. Once you take the trend away, then we know the variability. If you look at this, you find that when the world gets warmer, the variability is not necessarily large. In fact, this year, the variability is much stronger than that by comparison. So, in United States, the U.S. Climate Research Center, NCDC, National Climate Data Center, is start to embark on a new study of what is normal. Yeah, people always try to define weather as a distribution, a normal curve. 3 standard deviation away from a normal curve, it's terrible. But then they realize if you plot the probability curve, that implies that the underlying process is stationary. But the climate data is not stationary. So before I left, they asked me to give a talk there, and they will talk about a new term. The new term is called the dynamic model, a dynamic normal. Means it's normal, but the normal is more dynamic. It's keep moving. My sigmas keep moving. And they cannot define how dynamic is that dynamic model, a dynamic normal. This is what they will talk about. See, when you talk about variability, you have to have a reference. But that underlying reference may not be a constant. And that's where the dynamics come in. So, this kind of data has lots of implication on climate change, on climate variability, and all. So, if you look at this, then you know that the high variability is not particular to the current high temperature period. Now, after we look at this, after I analyze this data, another question comes to me. I said, how is this annual data derived? Or people say, oh, they have monthly data. This data is really serious. This data is not, this data has gone through thousands and thousands of hours of analyzing. Yeah. So I trace and I got the original data. This original data you can download actually from the Southampton data center. I downloaded this in 2003 when I did this work. And if you go now, you can probably get even more recent. What they got is that they take monthly data. This monthly data they collected from thousands of weather stations on the world. And this weather station will all have to have thermometer. You cannot just say, well, it's warm or cold. No, you have to give me a thermometer. And that thermometer has to be continuous. And see the thermometer, after you get thousands of thermometer data, then you average globally, you get this monthly data. Excuse me. So this line, green to us and red to them. The red line is actually the monthly data. The green line behind you, or here, I will refer to color over there so that they can listen. The green line you refer to, that is the line indicating how dense the data is. Yeah, how many data you put it in. Now you look at the beginning in the 1860s. The globe, the whole world is covered about less than 20% with the thermometer. The thermometer at 1860 is not that common. I almost guessed, ventured to guess, that at that time there perhaps is not a single thermometer in China. 1860, that's 150 years ago, almost 150 years ago. Yeah. But the whole world is covered only 20%. Now we are covered more than this 60. It's more than 80% covered. There are two interesting dips. If you look, the dip over here and the dip over here. There are two prominent dip of the global coverage. And if you look at the time, that's a very interesting time. The first part of that is around 1917 to 1920 or something. That's the First World War. And the second period is here from 1938-39 to 1945. That's the Second World War. During the war, people are busy doing other important things, killing each other. Nobody is manning the thermometer. So the data in these two periods are not as complete as other periods. So we get monthly data. And once you get monthly data, it's very easy to get yearly data, you think, right? It's very monthly, January, February, I add all this month and divide by 12. That's my annual data. Is that simple to get annual data? The answer is no. The reason is that if you use January plus February plus March plus April and all the way, what you did was exactly like you downsample the data 12 times. You take January, all January, plot a curve. Take all February, plot a curve. So you plot 12 different curves. Each one represents 1 month. So there's a whole year fluctuation there. Then you average at each point, you get this annual mean. So you have a downsample. Now we now know that if your data is noisy, your downsample is not going to give you a very good answer. So I decided to check how good the data is. How can you check that? It's very easy, because see, I can plot with this downsample. If you average, you will get this black line. The black line. The black line is the average of 12 months, and this yellow line is the upper and lower bound statistic. So I decide to check how good is this this downsample. So what I did here is I plot the average temperature of January, average temperature of February, March, April, June, July, and all that. Granted that they have already taken away the annual cycle. But as I said, as I demonstrate to you, how they take the annual cycle away, they use a fixed pattern to take it away. So the annual fluctuation, they never take it away totally. What it left is that they still leave some of the annual cycle here. The annual cycle, turns out, is that in the summer you have much higher. What did loss? We got picture. Hello, Tokyo. Can you hear us?
Yes, I can hear you.
Can you see the screen?
Yeah, no problem.
No viewgram?
Yeah, I can see the screen. So I can see the GSTA data.
The curve. Oh, so you can still see it. But yeah. Locally we lost your screen. The screen. So how about the Hiroshima?
Yes.
Yes. Okay. All right. So we'll just keep on going. 他们看得到。Maybe the bulb gets burned out. There's no lights. Yeah, that's all right. We'll just continue. They say they can see it. So you see that in the summertime the temperature is higher. The winter time temperature is lower. But the lowest the temperature is not January. It's March, and that's awkward. And another thing that makes me think that if we measured more than 150 years, we cannot even define the season. That means the data has a problem. Yeah. Not only that, let's see the variability of each month. I have 150 Januaries. So 150 January has a mean, which I plotted before. Now the variability of January, it's over here. And variability of summertime, July, August, is over here. In summertime, the variability is small. That's climate. Our summertime, our weather will never fluctuate very much. But in wintertime, it will. One of the reasons is that in wintertime, actually the specific heat of the air mass is much lower. It's cold and dry. So if front comes, the temperature can fluctuate wildly. But summertime, it heat up to like 35 degrees. How high can you heat it? How low can you cool off? Not much. So summertime, the fluctuation is very small. Wintertime, it can be very wide. Like I get this cold because the fluctuation of the weather in the last weekend. Anyway, so the fluctuation is very high generally in the wintertime, low in the summertime. But the curve is not smooth. Yeah, it's not that January is the highest. February is the highest. Yeah. All this indicate we have problem. So I decided to look at the data. I find that if I take that the full data, if I run a spectrum, what I see, the spectrum has a peak, and this peak is clearly 1 year. That means whatever they have done to take an annual cycle away failed. Why they failed? Because they used a cookie cutter, used a 30 years annual mean as a pattern. So each year is fluctuate a little bit, so you finally get the same annual cycle, just like what we saw in the CO2 data. So they get a peak. Beyond 1 year, there's almost no data, almost no information. Not no data, no information, because here it's almost flat. It's not exact white, but it's very, very noisy, and it's almost like a brown, or it's steeper than -1. Yeah, flatter than -1. So I decide that annual data is actually 12 to 1 downsample. So in spite of the removal of the climate data, there's still a seasonal peak. That's 1 cycle per year. Seasonal variation are somewhat irregular, and the data contains no information before yearly cycle. So I decided to filter this data using HHT. How do I filter it? I process the data. I process the data, and I use, at that time we have not got the ensemble EMD yet. So I process the data repeatedly, and I finally get to the 8 months. I take all the fluctuation of 8 months away, and if I take that away, what I took away, this is what we get left. That is, any change beyond 1 year, I kept it. Okay. All the rest are noise. Why they are noise? Because the noise is because of the unevenly data distribution and unevenly data reading. And when you have war, nobody read it. And when in the early time there's not enough distribution, all of that contribute to noise. So if we take that away and keep only the longer period, this is 8 months and a year and so on. So once you take that away, then you use HHT smooth the data. You find that HHT smooth the data compared to the original data. They follow the same trend, but it's much cleaner. And what's left? What do we remove? We remove this kind of noise, and the noise magnitude is not small. It's almost plus minus 1 degree. Yeah. So once we remove that, and we want to see whether that will change anything, it turns out the part that we remove, the spectrum looks like this. It's a white spectrum. So we remove white noise. In other words, we remove no information. And not only that, the original spectrum looks like this. And the clean up the spectrum looks like this green one, which is you go up and you go beyond 1 year, which is about 8 months, and then drop. So I successfully remove all the fluctuation shorter than a year. If you have fluctuation shorter than a year, then you downsample, you have alias. So once you remove that, and this is the cleaned up monthly mean. January, February, March, there are still 12 lines. and you compare this 12 line with the original 12 lines, you find that the cleaned up one it's much neater. Not only that, from the annual mean, cleaning up the annual mean, compare that annual mean to the original annual mean. They are different. How different? Most of the differences are here, are during this time, or during this time, or during this time. Yeah. At the beginning, there are not enough data, so there are lots of errors. Yeah. So, what is the total difference of this? The total difference is not much. The sigma is about 0.1 degree. But 0.1 degree doesn't look very big, but 0.1 degree, it's a lot in the global warming. Yeah. So, this is how I think it's a simple exercise to use HHT to clean up the data, to make the data look better. And how do I know the data is better? The total variation is smaller because I took the noise away. Not only that, the seasonal variation now becomes very smooth with the clean up data. As previously, the warmest time is July, but the coldest time is March. But now it's symmetric. It's very nice, very smooth seasonal. That means if I have observed the climate for 150 years, I certainly should know how good the seasonal variation is. Not only I see the seasonal variation, the seasonal fluctuation also looks more regular. And that gives me confidence of this clean up step is indeed make the data cleaner and more reasonable. So the global surface data anomaly should be derived from the simple average, because should not be derived from the simple annual average, because the original monthly data has a lot of noise. Yeah. So noise with period shorter than 1 year should be removed, because if you have a fluctuation over there, then you're going to cause some alias. Yeah. So smooth the data by remove period shorter than 8 months can actually improve the data just to produce much smoother annual average data. Now, I'm going to go through the last part of this, is that we start to look at the stock market. Okay, the stock market is NASDAQ. NASDAQ data looks like this. Now, if you take this NASDAQ data and analyze it with EMD, you're going to get 9 components, and that's it. Okay, the last one is clearly trend. Yeah, if you take this trend and you put this 1 component, 2 components, 3 components, 4 components, and so on, you eventually get to the full data. And if you plot this EMD determine the trend, it looks like this, and this is linear trend, and this is the exponential trend. No one will feed stock market data with a linear trend. Everyone knows the stock market grows at least exponentially. In other words, if I put the money in the bank, I will earn interest. The interest is compound, and so the growth is exponential. So the stock market should at least perform as well as I put the money in the bank. Yeah. Of course, there are fluctuations. Somebody win more, somebody lose some, but on average, it should be an exponential curve. And if something is go way beyond that exponential curve, that's a bubble. And clearly, this is a big bubble. And this bubble was the dot-com bubble in the United States. At that time, the NASDAQ hit about 5,000. Where's the NASDAQ now? 1,600. We're here. Yeah. This is overly. This is the present status because of the financial crisis. Yeah, here are the three different fits. Now let's look at the statistic of the three fits. If I use linear, after you take the linear away, you get the residual as this blue curve here. I don't know what the other curve looks like, but the Legends given here. And you use exponential. Exponential is the red, and use EMD is this. So there are three different residuals after you take away the mean. And what you see is that if you use linear detrend, the mean is exact zero. That is what the linear detrend will do. Linear detrend will draw a straight line, will give you zero mean. Yeah, but unfortunately, this zero mean doesn't mean too much. Yeah, and the standard deviation, however, is 560 almost. So the fluctuation is very large from that straight line. But if you use exponential is fine. It's on log curve, the mean is zero. But on the real data, the mean is not zero. Mean is 73. Yeah, 73 sounds bad, but it's not that bad because we're talking about thousands. The value is in the thousands. So this 73 is still acceptable. And the standard deviation decreased from 560 to 426. But if you use EMD, the mean is 0.3. A 0.3 versus 0. In this scale, it's almost 0. The standard deviation dropped almost half of that. So this means that if you want to draw an overall trend, a better trend is the EMD trend. Yeah, but whether EMD trend is good enough, perhaps not. But if you add a second term, that will go through a lot more, and for the second term you give a curve. That means the stock market has a cycle of 800 days. What's 800 days? 800 days is almost 4 years. The stock market doesn't open every day. It closes on weekends and on holidays and whatever. So it's about a little bit more than 200 days. Around 240, 250 days. So 4 years, it's almost like, this is almost 4 years. So stock market is a 4-year cycle. And that is interesting because a 4-year has another cycle, that's the president election. So whether the president play politics with financial policy or whatever, that's an interesting thing to study. Then if you add one more term, and that's even better. So then you have 400 days. So it's about 2 years cycle. And you can keep on doing this. Yeah, and this becomes 200 days. And so that's the trend, and it take a D trend out. But then I realized that whenever I look at this financial market, nobody uses EMD because EMD is not known to them. And what they did, you look at, I never watch the stock analyst in Taiwan. But occasionally when I switch channel, I see somebody will talk about, say, you should buy or you should sell. And they have a bunch of curves. And you pick up a newspaper, you have curves. What the curve looks like, the curve looks like this. Okay, this is the stock market. This is the curve. What are the meaning of the curve? This curve actually is the running mean. Running mean. The running mean, they have used 30-day running mean, 60-day running mean. Yeah. Now you think, if I use 60-day running mean, I will take 30 days before 30 days after. But in stock market, you never do that because you don't know the future. So you can only use the back. So this is back-looking 60-day average. So it's always always a time difference. So all this running mean looks very different from the data because the phase shifted. Okay, now this is 30 day, this is 60 day. So a lot of the stock market analyst has used this curve to give you advices. Now let's just say, okay, assuming we're analyzing it, we're not make a prediction. Let's say, giving that, let's say they can take future data and we just take off the line, not do real time. Then we can plot the running mean 60 day, 30 day all together. What you see is that EMD give you this color, EMD 4 to 9 give you this color fit, and 60 day give you that, 30 day give you this. Okay, if you make a comparison, you'll find that EMD actually follow most of the change much better than the 30-day average. Yeah. Then you ask, what's the time scale of C4 to 9? The time interval, time constant of C4 and 9, it's exact 30 days. Yeah. So if you take component 4 and beyond, you practically are doing a 30-day running mean. But we are not doing running mean. We're taking away the fluctuation. And that fluctuation, it has a mean of 30 days, but it's not 30 days. Sometimes much higher, sometimes it's almost 80 days. Sometimes much lower, almost 10 days. Yeah. So the stock market fluctuation has such dynamics that you cannot just say, okay, I will define 30 days, because time scale fluctuates so much. 30 days, when you come down here, 30 days doing nothing. When you come to here, 30 days smears everything. Yeah. So if you take the distribution of the time scale, the distribution of the time scale looks like that. 30 days is the mean, is the moments, the first moments. Yeah. It covers from, say, roughly 15 all the way to almost 80 days. When you take away from that running mean, from that EMD fit, this is the result. This is what's left. The fluctuation from that trend. And what you see here is extremely interesting. And what you see is that the fluctuation suddenly increased a lot. And this increase is higher as we get here.
Excuse me, Professor Fang.
Yes?
I cannot hear your voice.
You cannot? All right, can you hear now? Hello? Can you hear
Hello,
me now?
the Professor Fang.
Yes.
So I can see the screen, but I cannot hear your voice. So could you please check your microphone or something like that?
My microphone. How's now?
Oh, yeah, it's okay.
It's okay. Oh, the light.
Yeah,
is,
okay.
Okay, all right. Thank you. Thank you. Maybe my coughing scared off. Anyway, you can hear me now, right? So the
Yeah,
fluctuation.
I can hear you.
Yeah, the fluctuation is getting much bigger as we get closer. I tried to plot this beyond this time. It should be very interesting in the last few months, because I think the fluctuations go throughout the ceiling. Yeah, because now each day we drop 5% or something like that, right? So this is the fluctuation, and this is the little bit that in 1987 Greenspan caused a big shock in the stock market because one day he came out of the restaurant. The people, newsmen, very far distance, called him. He said, "Dr. Greenspan, what do you think of the stock market?" Dr. Greenspan said, "I cannot understand the irrational exuberation of the investor." Irrational means illogical. Exuberation means happiness because they make so much money, they become irrational. So then the newsman sent this news out. The stock market plunged 500 points on that day. Yeah, and that's very serious. And that's only this little bit. Yeah. And how to compare this fluctuation? You look at this fluctuation, maybe you think that the EMD fluctuation is smaller. The best way is to do a statistic. Hello? Hello? Okay.
Hello. Excuse me. So,
Can you hear me?
could you please check the microphone? I cannot hear you.
Can you hear me now?
Oh.
Can you hear me now?
The voice is not so clear, I think.
No. How about now?
Oh, it worked.
Yeah,
It's
okay.
working.
Okay.
Yeah.
Okay.
Okay.
All right.
Good.
I'm going to be very careful. I'm going to hold back my coffee.
Thank you.
Yeah. When you look at the distribution of the variation, you find that the distribution of the whatever left, it's much narrower by EMD than compared with all the others. Again? Yeah. I think you can hear me. Can you?
Yes, I can hear.
Yeah, they can hear. I'll hold this. Okay. All right. How about this? Yeah.
Yeah, it's good. It's good.
Yeah. Okay. So you can see that use EMD, you actually can get a better trend. We prove that we get a better trend because the fluctuation is much more. Oh, hello? Yeah.
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 Yeah. Okay.
I think that our microphone is a problem. Let me try another approach. Okay, hold on. Hello? Can you hear me?
The voice is not so clear, I think.
Oh, this is very, very loud in our side. How about here? Can you hear me?
Oh, yeah, it's good. Very nice.
Oh, very good. Okay. Now I have to tie myself to the podium. Okay. I'm going to stay here. So now we have next we're going to study the variability of the data. The variability in the data it's very important because you will calculate your gain or your loss or volatility of the stock market. So how to calculate that? There are various ways. One is by gain. That is, you compare your data, your stock market price today versus tomorrow. So it's each day by day difference. That means whether you make money or lose money, that's the gain. The other one is to define daily high and low. That means that on the trading of that particular day, what is the high price and what is the low price? And the difference between the high and the low price give you a measure of variability. I call it variability. I don't call it volatility because the stock market people think they have a monopoly of the word volatility. So I say variability. That's my definition. And variability of EMD is defined as the percentage of absolute value of the sum from selected IMF. Let's see. If I use C1, the first component as the volatility of the debt of the market, you will see that the Nasdaq data over the last until 2001 looks like this. That is, in that big shock caused by Greenspan, is really strong. It's almost 5%. That's 5% shock. And beyond that, there's another about 5% shock over here. Gain 5%, loss about 5%. Yeah, the rest of that is fluctuating. And the interesting thing you observe is that this fluctuation getting bigger and bigger. Why is it getting bigger and bigger? I think this is the contribution by the leading economists. The economists come up with some wonderful model to predict the movement of the stock market. I don't think it's right. But if everybody believes in them, then their prediction will be perfect. Yeah. And now enough people believe in them, so their prediction is getting better and better. And as a result, when everybody uses the same model, if the model says sell, everybody sell, the stock market will drop. Then after it drops, everybody says buy, then it's going to fluctuate. So the fluctuation increases because everybody behaves in unison. Yeah. And this I plotted as a variability as a percentage. So this is about 6%. If you use the current data, I think the current data will almost double this, because this go about 10%. Yeah. In fact, there are a couple of days that you get almost 12%. Yeah. This is measured by gain. Measured by gain, it's much bigger. It's 10% here. It's already 10% there. So the fluctuation is much higher, but the trend is the same. And this is high and low. So high and low is also very large, fluctuate very large. But by and large, it's still getting more volatile as we get closer to the present time. And and you look at the C1. What is the time scale of C1? Time scale of C1 means the stock market has a persisting time scale around 7 to 8 days. Yeah, but not exact 7 to 8 days. About 4 or 5. It has some sort of memory, and that works very well for this data up to this time. But I don't think it will work. I think recent financial crisis make this time stock market persistent time scale much shorter. I saw a lot of time that one day it increased, the next day decrease, and all with very extremely high percentage. Yeah. Anyway, the distribution of that is that you have roughly a 7-day time scale, and the shortest maybe 2 days, and longest maybe a month persistency. And so I start to try to plot high-low variability with price gradient. The price gradient is determined by the mean. If I plot a overall trend, this overall trend that I got is from that C4 all the way to C9. You take a derivative of that stock market, derivative of of the stock market price. If the gradient is positive, you plot the data over here. Derivative is negative, you plot over here. Positive means the price is increasing. Negative means the price is decreasing. Now what you see is that the daily high-low normalized. That means in percentage. When the price is increasing, the high-low fluctuation is very low. When the time price is decreasing, the fluctuation is very high. This is very asymmetric. And what it indicates is, I think, it indicates the psychology of the investor. When the stock market is increasing, everybody's happy. I will put my money there. I will make money. So you just leave the money and you enjoy yourself, not worry about it. When the stock market is going down, you think that, gee, should I leave it there? Maybe I should sell it, okay? And when you sell and buy and sell, and once you sell, you say, gee, this probably hit the bottom. You go current buy. Once you bought it, and then they decrease again. So the big fluctuation, big volatility is over here. This is from high-low. And this is from EMD. It's more dramatic in EMD. This, if you look at this center line, which is 0, this is increasing, this is decreasing. Obviously, it has much wider scattering. Then I said, well, if they all behave about the same, let me plot the GAN versus EMD, see whether there's any correlation. Absolutely no correlation. What I call this is shotgun pattern. I mean, just like you threw away a bunch of beans, it fall everywhere. And you try to plot the GAN and high-low, again, no pattern. But if you plot EMD and high-low, you start to see a little bit general pattern. And this is interesting because EMD is derived from high and low. Yeah, and high and low is also derived from high and low. So EMD and high and low has certain correlation, much better correlation than the shotgun pattern. But all of this, however, indicate that we have to look at some significance, statistical significance. So we take the GAN and decompose. We find that most of the data, the GAN fluctuation movement, are actually random. When this is random, it may fit and Engels and Granger. Because Engels and Granger think that the stock market is a random process. It's ARIMA is integrated once, you get the stock market. The integrating once, you get it from white noise to brown noise. Yeah. So, so the long term, however, is not white noise. And you use high-low, the long-term high-low, again, is not governed by it. It's not fall in this range. And EMD, of course, is the same. And you plot it all together, you find the long-term data are not really within the white noise range. And if you take only the long-term, then you see the long-term, they start to see correlation. And the long-term correlation, GAN versus EMD, you have correlation. And the GAN versus high-low, you get a correlation. And high-low with EMD, you get a correlation. So the short-term, the moral is the short-term data, short-term financial market is really behave like a white noise. And that perhaps is influenced by the white noise model, integrated white noise model that the people in the stock market. So by the way, the stock market now is not totally run by people who don't know mathematics. In recent years, in the stock market, you will find a lot of high-powered mathematician, physicist, engineer working there. Before I come back to Taiwan in 2006, I went to Caltech, and one of the Caltech alumni invited me to his company. He actually, at Caltech, he studied applied math. He studied the nonlinear wave propagation. I asked him, so which company are you working with? He said, I'm working with PAMICO. PAMICO is the largest bond company. So I went to the company, And his position is vice president. He introduced me a room full of people want to listen to my talk on my view of how to handle time series. And I asked each one to introduce himself to me before my talk. I found there are about 15 people. Almost everyone are from the top universities. Berkeley, Stanford, MIT, Caltech, University of Chicago, and nobody is majoring in economics or finance. Everyone is majoring in applied math, physics, engineering, EE, or whatever. Yeah, those people are now get into financial market, and once they get into financial market, they start to use a priori determining model. This whose model is the most powerful one? Whoever get Nobel Prize call the shots. At least right now, Ingalls and Granger is very, very influential in the stock market. Yeah. So in here, we establish a working definition of trend, and it's a function of local time scale. And we need the adaptive data analysis method to determine the trend and variability. Various variability should be compared, and we have made some comparison here that I introduced to you, and further study should be done. And I'm planning to conduct more study of the stock market of the last few months. I think that will be probably the most challenging, most interesting, the most dynamic non-stationary time series anybody can ever see. Yeah. So the conclusion: the trend is a local property of the data. It should associate with a scale. So when you talk about trend, don't let people just say, "Well, here is trend." You have to say, "Trend for how long?" Yeah, and trend should be determined adaptively. So you cannot have pre-selected function. You can, if you cannot determine good trend, then you cannot determine a good variability. The variability is vary from a reference. Yeah. So these are all tied together: trend, detrend, and variability. And that is what the one of our recent paper discussed for. And if you cannot download that paper, you can come to me. I will give you a hard copy of the data. So that will be the end of this class. Thank you very much. I'm sorry for the occasional drop-off. I don't know whether it's electronic or my coughing, but both should improve next time. All right, bye-bye.
Thank you very much. Bye-bye.
Right, bye-bye. Have a nice weekend.
Yeah, good.